This is chapter 3-2. This is recording number 7. Okay, folks, now this is the next topic is the so-called empirical, otherwise known as the normal rule. Now, I have no control over these names, okay? Both of these names are awkward, and let me explain why. Okay, well, first of all, you need to understand what the word empirical means. Now, I think this is good advice for all your classes. You really should be, when you're reading a textbook or you're in class, you should have a dictionary with you, a college level dictionary, because there's absolutely no way to avoid it. You're going to encounter words that you've never seen before. You know, I'm almost 70 years old and I encounter words all the time that I don't know what they mean. So it's impossible for you not to have this come up. And you just are stuck. And it's foolishness to not have a dictionary available so you can look up the words. Now, if you're on the internet, of course, it's great because Google has this technique or this feature where you can just type in the word define and then whatever word it is you're interested in, and it will just give you the definition. So that's what I just did, empirical. So when we talk about something being empirical, what we are referring to is something, some human affairs of some sort that is based on or is concerned with or is verifiable by observation or experience. Okay. Now, contrast that with something that is based on theory or pure logic. So empirical evidence is something that you observe. You do an experiment, you talk to people, you just observe it. Whereas if it's theoretical or if it's based just on logic, we don't call that empirical. We say that that's based on theory. We say that, you know, common sense would tell you this, or its logic would tell you this, or what have you. Okay, so here's another. Empirical evidence is information acquired by observation or by experimentation. Okay, all right. All right, so the word empirical here, the empirical rule, really doesn't mean, I don't know why they call it that. That just doesn't seem to make any sense to me. The other name for it, the so-called normal rule, that makes a little more sense because what we're going to see later on is that we have what's called a normal distribution. And a normal distribution kind of looks like this. So it makes sense in that way that, you know, it looks like the normal distribution looks like this. The problem is I don't like the word normal distribution either because the word normal, you know, typically, you know, the way most of us think about the word normal, we think about it as being something, well, that's what you expect. That's typical. Like you know, the normal age for people to move away from home might be 18 or 19 years old. That's normal. But it's not like it's bad if you don't move out at the age of 18 or 19 years old. It's just, you know, so I don't know why they use these terms. They must be historical reasons, and it's unfortunate because it can be misleading. In any event, this empirical, otherwise known as normal rule, that's what they call it. So let's just deal with it, okay? I'd rather call it, you know, the X rule or the, you know, something like that. In any event, here's the concept. This Chebyshev's theorem, we had some cartoons up here, okay? You see this? That's not very symmetrical, is it? In other words, you know, it's weighted over here on the left-hand side. Are there any others? I guess that's the only one. Okay, so it's kind of weighted over here on the left-hand side. Chebyshev's rule applies, and it doesn't matter what the shape of the distribution is. So it applies to any distribution, and it doesn't matter what the shape is. However, if you have a situation where the distribution is bell-shaped, and then sometimes we call that normal, and I don't like that term, but that's what we call it sometimes. But if it's bell-shaped, in other words, if it's symmetrical, then we have the following statements that apply. It's called the empirical rule. Okay? Approximately 68% of the data values will fall within one standard deviation. So let's take a look at the cartoon here. So here's our X bar. Here's our one standard deviation right here. plus or minus 1 standard deviation, about 68% will fall between plus 1 and minus 1 standard deviation. 95% will be in this interval. It will be in the interval plus or minus 2 standard deviations. And then 99.7% will be in the interval x bar plus or minus 3 standard deviations. So between here and here, you've got 99.7%. Okay, so that's what this is all saying. All right, so we have an example here. There's a mean of 480, a standard deviation of 90. If they're normally distributed, then approximately 68 will fall between 480 plus 90, which is 390, 480 subtract 90, which is 570. So you see that's where he gets those two limits, the upper limit and the lower limit, okay? All right, so work your way through the arithmetic there, and you'll see what he's saying is correct. That gives you an idea of where the data is going to be, and that has a variety of uses. So we'll see later on. Okay, a very important caveat. Do you know what the word caveat means? If you don't, look it up. But basically, what caveat means is warning or concern. Or I'll tell you what. Let me look it up for you. I just love Google. I love Chrome. So we define caveat. It's a Latin word. It means a warning or a proviso. A proviso is some condition. If you say that there's a proviso, it means, well, hey, listen, provided you're 21 years old, you can come over to my house and have a beer. Okay, that's a proviso. Okay, so a warning or proviso of specific stipulations, conditions, or limitations. Okay, so you may have heard the expression caveat emptor. It's a caveat, and then emptor is E-M-P-T-O-R. Caveat emptor means here it is. Caveat emptor, it means let the buyer beware. Okay, it's a very common expression in the law. We say, hey, listen, you're a grown person, you're a grown up. You should have been more careful. Caveat emptor, let the buyer beware. You got to do your own. You got to check things out. Okay, so anyway, the empirical rule is a little bit better than the Chebyshev's theorem because you can be more precise. It's not, there's more restrictions on the empirical rule. You have to have these conditions. It has to be more or less symmetrical, okay? It has to be more or less bell-shaped, okay? But it gives you much finer details, okay? Because if you'll remember, see, this is saying within, it says 68% will fall within 1 standard deviation. Let's do 68%, whereas in Chebyshev, I'm sorry, 95% of this data value will fall within 2 standard deviations. What did Chebyshev say? Chebyshev's theorem said at least 3/4, so at least 75% will fall within 2 standard deviations. So do you see how the empirical rule gives us a little more information? Chebyshev says, well, it's going to be 75% or more, whereas the empirical rule doesn't say, well, it's this amount or more. It says, hey, listen, this is it. It's about 95% will fall within 2 standard deviations. So the empirical rule gives us more information, more definitive, specific information, more definite information, but the requirement is it has to be more or less symmetrical. It has to be more or less a normal distribution. Whereas Chebyshev is applicable, it's useful, it helps us regardless of the shape of the distribution. All right, so enough said about that. Now here's another concept, the so-called linear transformation of data. Okay, a transformation just means that you are changing the data value. So for example, you got a temperature value. You collected the data from Canada. Well, you may or may not be aware of this, but the United States is about the only country in the world that uses Fahrenheit for temperature. The United States is also, I believe, the only country in the world that uses inches anymore. Everybody else is using a metric. At one point in time, I think it was Liberia that also used inches, but everybody else in the world uses the metric system. And so you have to transform, you have to change the data. If you collected temperatures from Canada, they're using Celsius, and we over here in the United States, who the heck knows what that is, right? None of us think about it in those terms. We use Fahrenheit. So this is a transformation of the data. How do you transform it? I don't know. Look it up on the internet. But there's a way of transforming it, okay? All right. So how does this linear transformation of the data, how does it affect the mean and the standard deviation of the data values of this whole distribution that you have? If you started in Celsius and you then converted everything over to Fahrenheit, how does it affect it? Okay, so that's the issue. That's the question. All right, so here's an example. You got this small store. You have 5 employees. Here's the hourly salaries. You can take a look at that. Okay, add them up and then divide by 5. You get an X bar of 12. Standard deviation is 2.5. Okay, you have a good year. I'm going to give everybody a raise of $1 per year. What's the new salary? Here it is. Well, the new mean is going to be X bar of 13. Well, what happened? You added $1, so X bar went up by $1. Okay. What's the standard deviation? The standard deviation, oh my goodness, it's still the same. It's 2.5. Why is it still the same? It's because standard deviation measures the dispersion. Everybody went up by $1. It's not more dispersed. It's not more variable. It's exactly the same variability as before. So the mean increases by the amount that was added. The standard deviation does not change. Okay. On the other hand, let's say you have number of hours that they work. Okay, the mean is number of hours is X bar is 15. The standard deviation is 4.123. Okay, we're going to double the amount of each employee's hours. Okay, how does it affect the mean? Well, you multiply by 2. The mean is doubled. It goes from X bar of 15 to an X bar of 30. The standard deviation goes from 4.123 to 8.246. So when you multiply, the mean and the standard deviation also double. Okay, so if you multiply by 2, it goes up by 2. If you multiply by 3, it goes up by 3. So bottom line is, when each of these data points, each of these data values is multiplied by a constant, the mean, it will be equal to the constant times the mean of the original set. We call that a linear transformation. If you multiply by 3, everything is increased by 3. Multiply by 4, it goes up by 4, okay? All right. Now, here's a nuance, I guess. The standard deviation will be equal to the absolute value. That's the positive value of the constant. So if you multiply by -3, you convert that to the positive value. Okay. All right, blood pressure. Oh, I'm sorry. Here's the applying the concepts. I know everybody's busy. Everybody is so busy, and a lot of you folks have kids. A lot of you have jobs. I know how horrible it is, but do the best you can. If you can, look at least look through these applying the concepts. They're very, very helpful. They help you really put it all together. Okay, so now that's the end. That's the end of recording number 7, and that's the end of chapter 3-2. So we're done with 3-2, and as I do recommend, however, that you look through some of this material on your own. Okay, well, thank you.